Hi guys, welcome to another video. So today we're going to be looking at the core pure chapter module, and in particular we're going to be looking at basic complex numbers. So you've already seen in GCSEs that when you have a negative square root, it's a bit of a problem. We don't get a solution. So in GCSE you come across this quadratic formula. Okay, and the bit in the square root is known as the discriminant. And now in the A-level maths, you would have used discriminant to find out how many solutions there are. So we said if b squared minus 4ac is greater than 0, we have two real roots. If it's equal to 0, it has one real root. And if it's less than 0, we said no real roots. And the problem is there was no real roots because you can't square root a negative number. So this is where we left off after A-level maths. So to solve these equations, we need to use this imaginary number, and we'll call it I. Now I is used in maths for imaginary, but when you go to university and start engineering, it's commonly used as J, because they use I for current and that sort of stuff. So whether you use I or J notation, it makes no difference. So I is actually square root of -1. Okay, and the imaginary number I can be combined with real numbers to create what we call a complex number. An example of a complex number would be 5 plus 2i. And complex numbers can be added, subtracted, multiplied, and divided the same way you do with algebraic expressions. So if I say, here's a complex number, a plus bi, where a is a member of real number, b is also a member of real number, and I have this set of complex numbers. So if I add these up, you basically group them together. So you do 2 plus 7 gives us 9, and 5i plus 3i which gives us 8i. If we look at this one, 2 minus 5i, and we're taking away 5 minus 11i, same as before. If we multiply the bracket with the second one, because we have to be careful, minus times minus, so it gives plus 11i. And if we group them together, we get minus 3 plus 6i. And we've got another one, 6 bracket 1 plus 3i. We multiply the bracket, so it'll be 6 plus 18i. So let's write square root of -36 in terms of I. So if we split this up, we can write this as root 36 times root minus 1. And we said how square root of -1 is I, so this will be just simply 6i. So why don't you guys have a go at this? Write square root of -28 in terms of I. So same as before, we can split this up. We have root 28 times root minus 1. Root 28, the highest squared number that goes into it is 4, so we could write this as root 4 root 7 root minus 1. Now root 4 is just 2, so that'll be 2 root 7i. So we could write this just as 2i root 7. Now let's solve this one. X squared plus 9 equal to 0. In the past, you would have said there's no solution and moved on, but now we know complex numbers. We could work this out. So if I take 9 on this side and square root, I have a plus or minus square root of minus 9. So again, I could split this up. So I have root 9 times root minus 1. So that will give me the following. X is equal to plus or minus root 3i. So plus or minus 3i. So let's have a look at another quadratic. X squared plus 6x plus 25 equal to 0. You could use a couple of methods on this one. you could either complete the square or use quadratic formula. We'll use completing square on this one. So why don't you guys pause the video and have a go at this, complete the square. So when you square root, when you complete the square, we need to put x plus 3 squared, and x plus 3 squared gives us x squared plus 6, x plus 9, but we want plus 25. So we simply just add another 16 on, and we equal it to 0. Now straight away you see we have a plus 16, so by subtracting it we go negative, and then we square root, and now we know our complex numbers. We could start square rooting negative 16. First we'll take the plus 3 on this side, so it becomes minus 3. Our square root of 16 is 4, so we'll have x equals to minus 3 plus or minus 4i. And if you use the quadratic formula, a equal to 1, b equal to 6, c equal to 25, substitute into the quadratic formula, and you will see it gives you the same answer. I just written it slightly different. You start off with x equals to minus 3 plus root, so minus 3 plus or minus 4i. So we're going to continue with complex numbers. So last lesson we looked at how to add and subtract using complex numbers. So today we're going to be learning how to multiply and divide using complex numbers. Now if you recall, I is just square root of negative 1, so I squared is minus 1. So if we have to multiply these two set of complex numbers, you just simply multiply out like how you do using FOL method. So when you multiply out, you get the following. So now we know that I squared is equal to minus 1, because if I is square root of minus 1, if we square both of this, I squared would equal to minus 1. So that means this bit here, 15i squared, will be 15 times minus 1. And now if we tidy that up, we get minus 7 plus 22i. Okay, so why don't you have a go at this? Okay, so with this one, the squared simply means you can have two lots of these. Same as before, if you expand this using FOL method, and now we know 16i squared is just going to be minus 16. If we tidy this up by simplifying, we get 33 minus 56i. Okay, why don't you guys pause the video and have a go at this question. Okay, so if we start off by multiplying the first two brackets, use FOL method, expand this, and then simplify. 39 squared is minus 1. So if we tidy this up, we get minus 7 minus 22i. And now if we just multiply that with the third one, so you multiply out again using FOL method and tidy this up, and you should get 59 minus 43i. Okay, so I cubed. We split up I squared times I. We know I squared is minus 1. So minus 1 times I. So I cubed simply is equal to minus I. I to the power of 4. We could split this up as I squared times I squared, which is minus 1 times minus 1, which will just give you 1. Two I to the power of 5. So again, we could write this as 2 to the power of 5, I to the power of 5, using indices rule. Now, 2 to the power of 5, you just could work that out separately, but what's important here is the I to the power of 5, which is I squared times I. Now we know I squared is minus 1 times I, so it will be 32i. So if a complex number is given by let's say z equals to a plus bi, then the complex conjugate is z star equal to a minus bi.
Yeah.
So we have to reverse the sign of the imaginary part. Together these are known as complex conjugate pair. So we could write, for example, 2 plus 3i, if we reverse the sign, as 2 minus 3i. So that's the conjugate pair. If we have 5 minus 2i, we could write this as 5 plus 2i. That's the conjugate pair. If we have 1 minus I root 5, we could write this as 1 plus I root 5. So we want to find z plus z star and z star, given that z is equal to 2 minus 7i. So z star must be 2 plus 7i. So z plus z star is simply going to be 2 minus 7i plus 2 plus 7i. So if you group them together, we'll have 4, because minus 7i plus 7i will cancel out. Now z and z star, so the product of the conjugate pairs, we're simply multiplying 2 minus 7i with 2 plus 7i. And as in the previous slide, we simply multiply these out using FOL method. We look for the I squared, replace that with minus 1. So our final result will be 53. Okay, so why don't you guys pause the video and have a go at this one. Okay, so we know what the conjugate pair looks like, and simply add them together. And if we collect the integers together and the imaginary, we just get simply 4 root 2. And for the product of the conjugate pairs, we just multiply this using FOL method, tidy these up. Remember, I squared is minus 1, so we just get 10. So here's another example, and this time we're going to divide two complex numbers. With divisions, you need to multiply both the numerator and the denominator by the complex conjugate to the denominator. So, for example, here we're going to multiply by 1 minus 2i over 1 minus 2i. Bearing in mind this number here has to always be 1, so the top and the bottom must be the same. So it's very similar to what you do when you rationalize the denominator. You multiply the denominator, the conjugate pair, so you do the opposite sign in the middle, just like what you'd have done rationalizing surds. So if we multiply the top together and the bottom together, so now the top we know you just simply FOL method and tidy this up, and the bottom, well, we should have got the hang of it now. That you'll see when you multiply the conjugate pairs, there won't be any imaginary left. So what we're left over with is the following. So on the numerator we have 20 minus 15i over 5. And now if we divide all of this by 5, we get 4 minus 3i. So why don't you guys pause this video and have a go at this question here. So same as before, we're going to multiply top and the bottom by 2 plus 3i. So if we multiply the numerator and multiply the denominator, now we just need to simplify this by grouping the I components together. So we get minus 2 plus 23i over 13. Now if you want, you could write this as minus 2 over 13 plus 23 over 13i. So we're given minus 1 is the root of the equation. So we have a cubic equation. We want to find the other two roots of the equation. Now, you would have covered some of this in factor and remainder theorem in normal A-level maths. So with the factor and remainder theorem, it says if you know the root, you can simply substitute it in and show that it's equal to 0. So if we replace x with minus 1 and tidy up, we get k equal to 5. Now we know the k value, we could rewrite this cubic equation as x cubed minus x squared plus 3x plus 5 equal to 0. So now that we have the cubic equation, we can now solve the cubic equation. And there's two ways you could do this. One is the identity, or you could use the long division. So here I'm going to use the long division method. We know minus 1 is a factor, so it must be x plus 1 that we divide this by. So we want to see how we could make x cubed. So you need x squared at the top. Now if you multiply x squared by x plus 1, you get x cubed plus x squared. So if we minus this, x cubed cancels out, minus x squared minus x squared, so minus x squared plus minus x squared gives you minus 2x squared, and we still got plus 3x plus 5. So now we want to make minus 2x squared, so we'll put minus 2x at the top. Minus 2x times x plus 1, it gives us the following, minus 2x squared minus 2x. Now if we subtract these, we get 5x plus 5. So now at the top, I know I need another 5. So 5 times x plus 1 will give me 5x plus 5. And that's equal to 0. So we've got our quotient, which is x squared minus 2x plus 5. So now we could say this this cubic equation can be written as x plus 1, x squared minus 2x plus 5. We already know one of the roots, so to find the other root, we need to simply work with x squared minus 2x plus 5. So now we set this equal to 0. We could do this by completing the square, because we like this even number of 2x in the middle. So if we complete the square, you get the following. And if we take 4 on the other side, now in your A-level maths, you would have said there are no solution and moved on. And now we're doing further maths and we understand complex numbers. Well, we could square root negative 4, which is plus or minus 2i. So I simply add the 1 on the other side. So the solution of the equation, of this cubic equation, are x equal minus 1, x equal 1 plus 2i, or x equal to 1 minus 2i. So in a cubic equation, either all three solutions are real, one solution is real and the two other are complex conjugate pairs. So you could solve some types of polynomial equation with real coefficients. So if you have a quartic equation, so quartic equation has power of 4, and you could have total of 4 roots. For quartic, you could have all 4 roots are real, 2 roots are real and 2 are complex form of conjugate pairs. Or you could have all 4 roots are complex and form 2 complex conjugate pairs. So let's take this example here. We're told 3 plus I is a root of quartic equation. So here's the quartic equation, 2x to the 4 minus 3x cubed minus 39x squared plus 120x minus 50 equal to 0. So as one of the roots is 3 plus I, we know the other root must be 3 minus I. So we can use this to find an expression which will factorize into the original equation. So same as before, if we add them together, 3 plus I plus 3 minus I, we get 6. So the b term is minus 6. If we multiply them, 3 plus I, 3 minus I, and tidy up, we get equal to 10. So the c term is 10. Now you know b and c, you could write the expression and that will divide the original equation. So x squared minus 6x plus 10 will divide the quartic equation. So we could quite simply do the long division, because we know x squared minus 6x plus 10 is a factor. So if we do a long division of that, okay, we should be able to work out what the quotient is. So why don't you guys pause the video and have a go at this. So we start off with 2x squared at the top, multiply x squared minus 6x plus 10, and then take this away. Now we need to make 9x cubed. So at the top we need 9x, multiply out, and then we take this away. So we got minus 5x squared plus 30x minus 50. Now at the top we need minus 5. Minus 5 times x squared minus 6x plus 10 will give us the following. We take that away, and that gives us 0. We have now factorized the original equation into two quadratic. So this quartic can be written as product of two quadratic. So what we simply do is just solve each one of these quadratic. So if we take the first one, we know it's going to be 3 plus I, 3 minus I, because that's how we got the first quadratic. For the second one, we need to solve this. So if we factorize this, 2x minus 1, x plus 5. So x equals to half, or x equal to minus 5. So this quartic equation, the solutions are x equal 3 plus I, x equal 3 minus I, x equal half, or x equal to minus 5. So all this will give you an answer 0 when you substitute it in.